Hello everyone. I am Mrs. P. Shampi Chellaya. I am going to take linear integrated circuit, the topic on Unit 3 analog multipliers and PLL. First, we will discuss the principle of an analog multiplier using op-amp. What is an analog multiplier? It produces an output voltage that is proportional to the product of two independent input voltages. The two most common op-amp based techniques to achieve the analog multiplier are the logarithmic summing technique, emitter coupled transistor pair, and variable transconductance technique. Now we will discuss the principle of logarithmic summing technique, which is used to achieve the analog multiplier. The circuit typically uses three main stages: the log amplifiers, summing amplifier, and an anti-log amplifier. Two log amplifiers are used, which is configured with a diode, and it converts the two input voltages V1 and V2 into logarithmic of the voltages V1 and V2. The input voltages are applied to log amplifiers. The summing amplifier adds the logarithm of the two input signals together. The sum is given to the exponential form, resulting in an output proportional to the product of the two original signals, and this is achieved using anti-log amplifier. Thus, the analog multiplier is implemented using the logarithmic summing technique. Technique to implement the analog multiplier is emitter coupled transistor pair. The previous logarithmic summing technique is single quadrant multiplier, and we have some limitation, that is, due to temperature variation, the log amplifier characteristics will vary, which results in erratic error voltage. Hence, we go for the next type, emitter coupled transistor pair, which is a two-quadrant multiplier. Here, in this emitter coupled transistor pair, it consists of two matched transistors with their emitters tied together and connected to a shared constant current source. This versatile circuit configuration forms the fundamental building block of op-amp, analog multipliers, and emitter coupled logic. So, how it works? The collector current varies exponentially with the input voltage as per the transistor equation. The output current is proportional to the multiplication of the signals. Instead of turning a transistor fully on or off, this circuit steers a fixed total current IEE between the two branches depending on the difference in base voltages. When a small differential voltage is applied to the base, which is at the base of the two transistors Q1 and Q2, the circuit amplifies the difference between the two signals, whereas it rejects the common signals. Analog, if the base current varies proportionally with the second input voltage, the circuit will act as the analog multiplier. Because it operates in a non-saturated region, it is used for building ultra-fast digital logic gates and clock distribution circuits. Continuing with the working principle of this emitter coupled transistor pair, it relies on current steering and the exponential relationship between base emitter voltage VBE and the collector current IC, as shown in the previous circuit diagram. In the balanced state, if identical voltages are equal to both bases, the shared current IEE divides equally between Q1 and Q2. Each transistor carries a current of IEE by 2. In unbalanced state, when a small voltage difference is applied between two bases, the base of Q1 is slightly higher than the Q2, that is the VBE of Q1 increases. Because of the exponential nature of BJT, Q1 begins to conduct much more current, pulling the common emitter voltage up. The rising emitter voltage reduces the VBE of Q2, causing Q2 to conduct less current. Eventually, if the voltage difference is large enough, Q1 absorbs the entire IEEE current and Q2 is driven into cutoff. The key characteristics are considered as the differential amplification and common mode rejection, which amplifies the different signal and rejects the common signal. It is commonly used in Gilbert multiplier cell. Now we will discuss the next technique, variable transconductance technique, which also implements the analog multiplier. This uses transconductance variation of transistor or OTE. The output current depends on GM, which is the transconductance, and the input voltage Vin. The GM is controlled by bias current. It is an electronic circuit that produces an output signal proportional to the product of two input voltages. It is achieved by using a differential amplifier where the transconductance GM of the transistor is dynamically adjusted by one of the input signals. Now we will discuss the working principle of variable transconductance. The circuit is shown, which is designed using one emitter couple, and it is another voltage is given to the emitter bias transistor. The one signal controls the transconductance, another signal is applied as input voltage. The product obtained is output current or voltage. The transconductance of a bipolar transistor is directly proportional to its emitter bias current IE. The input Vx is applied as differential voltage to the base of the input transistors. Input 2 Vy controls the emitter bias or current of the differential pair. Because the gain, that is the transconductance, is proportional to IE, which is controlled by the second voltage Vy, the resulting output current is effectively the product of Vx and Vy. So the output equation Vout is given as R1 by Vt Re into Vx into Vy, where RL is the load resistance, Vt is the thermal voltage, and Re is the emitter resistance. So mainly the common configurations are two quadrant multiplier and four quadrant multiplier, which is a Gilbert cell. The two quadrant multiplier controls the trail current to allow multiplication for varying polarities of one input voltage. The advantages of variable transconductance technique of circuit operation, low power consumption, and it is suitable for high because the various technique to implement the analog multiplier. Thank